a pleasure to be here. My wife Susan is here with me. She's been a long-suffering attendee of talks like this for our 40 plus years of marriage. So I'm grateful for her to take yet another one. This may be the one that breaks the camel's back. I don't know. We'll see. We live in Atlanta. I grew up in Chattanooga and got interested in astronomy as a grammar school kid there, and grew up at the Clarence T. Jones Observatory, almost literally, if you've ever visited there. Built in '36, even older than Oak Ridge National Laboratory, also due to Franklin Roosevelt, as a matter of fact. But anyway, I've been interested in astronomy all my life, and when I was in graduate school at UVA, my advisor, who was involved with a project that all of you know of today as the Hubble Space Telescope, was then called the Large Space Telescope. The Large was dropped when NASA cut the budget and the aperture by about a third, and it just became the Space Telescope. But Larry Frederick told me, don't ever get involved in the NASA project. It takes forever to get anything done. So I took his advice seriously, and I got involved with a ground-based project that took forever to get anything done. But anyway, I'm delighted that I can report that it's working really very, very well. So when I got my PhD, I got a job, a postdoc at Kitt Peak National Observatory in Tucson, Arizona, and this was in '75. There was a brand new technique that had been dreamed up by a brilliant Frenchman who was sort of always the bridesmaid but never the bride in the Nobel laureate business. He was nominated a number of times but never got it. But he invented a technique called speckled interferometry. And his first paper was published in '73, and I got a job in '75, had a brand new 4-meter class telescope, 4-meter telescope on Kitt Peak. And I worked for a guy who was the principal scientist on that telescope project. And I got tons of telescope time for a few years, and then continued to get time on that telescope and others for many years using this high-resolution speckle technique to look at double stars. And it's a technique that allows you to achieve the full diffraction limited resolution of a telescope, in this case of an aperture of 4 meters, from the ground by freezing out the atmospheric turbulence in a process that was sort of misnamed speckled interferometry. It's better called speckled imaging. So I started off looking at binary stars, and in those days, binaries were the last objects that astronomers looked at and actually made measurements with their eyeballs at a telescope using what was typically referred to as a Fowler micrometer. And so the astronomer would go to the telescope, typically classical refractor of, half meter to, a half meter was sort of standard 24, 26 inch refractor. And these binaries, the closest binaries that they could resolve would have angular separations of maybe a quarter or maybe even 0.15 arc seconds, which is very close. And these people had really good eyes, and they were doing sort of speckle in their eyes and their brains. But so these very devoted observers would look at binaries, and they would take a measurement. 5 years later, they would come back again, and it basically would be in the same position, maybe have moved a little bit in its orbit. And so these devotees would make these measurements, and they would leave them to the third generation later to calculate the orbit once it had, 500 years later gone around once. And I found resolving binaries wonderful work, and with the 4-meter telescope, I could go down to stars as closely spaced as 300ths of an arc second, which sounds fabulously close, but I'm going to show you some in a few minutes that are much closer than that. But I felt, wouldn't it be nice to be able to see a binary go around before you're dead, and you could actually calculate the orbit? And so I always dreamed of having really high resolution techniques. And around 1983, the technique of long baseline interferometry was beginning to develop. And interferometry is a technique that was developed long ago. I'm sort of getting ahead of myself here. But the point is that my motivation for doing what we did at Georgia State with the Center for High Angular Resolution Astronomy was to be able to look at close binary stars that move around quite rapidly. And I'll show you some nice examples of that tonight. So here's an outline of my talk. And I'm not going to read it to you. That's the worst thing a speaker can do, is read the transparencies to you. And I'm going to end. John sort of opened up, and I feel like I am in good company here to talk about a little bit about my writing efforts, which actually got started sitting on airplanes flying back and forth from Atlanta to California to kill time. I always hated to watch movies and never was very sociable to talk to my neighbor on the airplane. But so let's get going here. So you all know why we build large telescopes, and Most astronomers are interested in sort of the larger scale universe, galaxies and cosmology and things like that. And so they want to have larger and larger telescopes so that they can collect more light and see farther away in the universe, see the distant objects in the universe, see remnants of the early phases of evolution in the universe and so forth. And you all know that, so they're after light gathering power, and that goes as the area of the telescope aperture because it's a light bucket. And so if you double the diameter of a telescope, you get 4 times the light gathering power. And there's a lot of effort nowadays to build super telescopes. Back when I was a kid, and most of you remember for a long time, the big famous telescope was a Palomar 200-inch, 5-meter aperture, beautiful telescope. And it's a very impressive telescope to see if you've ever seen it up close. It's much more impressive to look at the 5-meter Palomar telescope than it is to look at the 10-meter Keck telescopes, which look like big garbage cans to me. They're so short focal length, they're just stubby things. But this thing's an F5, and it's a beautiful long telescope. You can't see it there well, but these are sort of produced at the same scale, and this is one of the several large telescope projects currently underway. The Europeans have done a better job sort of getting their ducks in a row because it's a multinational enterprise. And so the European Southern Observatory is talking about building this extremely large telescope with an extremely bad name, in my opinion, the ELT. And in this country, there's the Giant Magellan Telescope Project, which is a private project by the Carnegie Observatories, Carnegie Institution of Washington. Caltech has one called the 30-meter telescope. And these are all $500 million to $1 billion telescopes. Telescopes like this are expensive, and there are cost curves that tell you, here we go. I just looked this up. The current cost of the ELT is about 1.1 billion euros, and the dollar has done a little bit better lately. Last time I gave this talk, it was $1.5 billion. Now it's only 1.2 billion, so it's a bargain. But that's a lot of money. So keep that figure in mind. The other reason to build a large telescope, which is the reason that motivates me, is that as Dave and I were talking in the back a bit ago, the larger the telescope, in principle, the higher the resolution. And the angle that you can resolve decreases in direct proportion to the increase in the diameter of your optics by the Rayleigh criterion of 1.22 lambda over d. So you can ask yourself, if you're interested, if you're motivated by finding out about stars, how big a telescope do you have to build to be able to see? The point is that if you want to look at stars and resolve a star like the sun and see spots on its surface, you have to build a telescope not 30 meters, but hundreds of meters in diameter. And the cost of those telescopes is, well, astronomical in the sense that you can spend $1 trillion, and the Defense Department wants your money rather than the National Science Foundation ever getting it. So in order to build a really super telescope to achieve higher resolution, you can't do it in a classical way. Even if somebody gave you $1 trillion to build a telescope like this, the technology just doesn't exist. It would be materials technology, the engineering just isn't there. It's an enormous civil engineering project to be able to do something like this. So you have to cheat. So let's say you want to start out and you want to mimic a 400-meter diameter telescope, and you don't have $1 trillion, you have a handful of millions of dollars, which sounds like a lot of money. To me it does, to others it might not, and I won't make any political jokes about that right now, but in other words, if you're confronted by realities of dollars and engineering, you mimic producing a single large aperture telescope by taking small pieces of that aperture and putting an individual telescope in those locations. The trick that you have to do, and the way I like to put it, is you fool the starlight. So you have starlight coming in from some distant target, and in order to produce an image, and in order to achieve this Airy criterion, or Rayleigh criterion in it, you have to bring the starlight to a focus as if the entire wavefront is striking the surface of a parabola. Now, if you have telescopes on the ground, you say have 6 smaller pieces of that telescope. You want to make the starlight thinking each of those 6 pieces is actually attached to a parabolic mirror, 400 meters in diameter. You can do that by having telescopes up in the air that you point around in different directions. but that's kind of awkward to do, and so there's a cheaper, easier way to do that. So you ditch the idea of this 400-meter diameter mirror. You got 6 telescopes on the ground, and then you bring them together in a central laboratory with a good deal of complexity involved, and it works as if it is this single large diameter telescope for the purpose of resolution, not for light gathering power. You've only got 6 little telescopes, so you're not seeing edge of the universe things here in terms of sensitivity. This is actually a cartoon that shows what we built on Mount Wilson, how it sits in. The big dome in the middle is the 100-inch telescope dome, and the lower left is the 60-inch telescope dome. Susan is very familiar with all this. She's been out there probably 100 times with me over the years, and she used to, if you ever rented a night on the 60-inch, you would deal with my wife for about 10 years to rent it, and she was great. She would never reduce the cost, though, I can tell you that. She raised a lot of money. So this is what we did, and so let's give you an idea of the size of this footprint on the ground. Here's a Google Earth map of this area. We are here where it says we are in the Grove Theater, and that's the footprint of the extremely large telescope mirror on the ground. So that's, you could put that in a shopping center somewhere. All the atmospheric conditions wouldn't be appropriate to it. So let's put it over here. We'll tear down this house, and the government will write them a check like they did the people in the community long ago to take the property. So there's the European Large Telescope gotten out of the way, and here is the CHARA telescope footprint on the ground, the equivalent telescope that we built on Mount Wilson. So it's big. I often do this with a picture of downtown Atlanta, and it interrupts a lot of real estate in downtown Atlanta. So 400 meters, about a quarter of a mile, and so that's the size of the telescope we built. So I have a couple of silly slides that I'll go through quickly to give you sort of analogies to the resolution you can achieve. So you look at your pinky finger at arm's length, and that subtends an angle of about 25 arc seconds. How far would you have to view your pinky to have that same angular diameter as Mars? You can do the simple trig. It's about 83 meters away. So look at somebody else's pinky finger nail rather than snipping off your own. And so that's the angular size of Mars. So again, with that same analogy of the size of your pinky finger, a physical size of 1 centimeter, then Altair, which was the first star whose surface was ever imaged by a telescope, which was our telescope about 10 years ago, 11 years ago now, you would, it has a diameter of 0.003 of an arc second, which is pretty small when you think about it, but it's actually not near the limit of resolution we have. And you'd have to move your pinky finger almost 700 kilometers away. That's the equivalent angular diameter that subtends. But we can see actually detail finer than that. So forget the pinky finger. So our limiting resolution is about 1/10,000th of an arc second. Tiny, tiny angle. It's about the angular size of a nickel at a distance of 10,000 miles. That's my standard blurb about that. And so what is the smallest dimension CHARA could resolve on Mars? And in fact, it turns out that the smallest dimension is, we could resolve ourselves. If the Martians built an interferometric array on Mars, we could resolve it. And Marvin the Martian here is very impressed, but then he says, is there a caveat? And the answer to that is especially fitting here in Oak Ridge, because I say, well, the problem is that there's not enough illumination, and you'd have to do a thermonuclear air blast to provide enough illumination of the scene so you could see it. But if you can make it bright enough, you could see it, but it would take a lot of photons to light it up. And that's a problem with interferometry. Interferometry has higher resolution than sensitivity, so that we can in principle see stars very, very far away and resolve them, but they're so far away they're not bright enough to be able to see. Okay, now interferometry is not easy. And this diagram shows why it is not easy. Basically, to fool the starlight and to invoke the physical principles in optics that produce optical interference fringes, you have to bring the two beams of light from two telescopes together. If you see down at the bottom it says fringe position. You have to bring the two beams together, compensating for the fact that the light coming in from the star, the wavefront is striking telescope 1 before it strikes telescope number 2. You actually have to compensate for that distance, that delay, which is equivalent to lifting telescope 2 up in the air and putting it up there at that wavefront as if it's a piece of that parabolic mirror. If you don't do that, it doesn't work. It's the same thing if you have two little parabolas and you take them and you collect starlight and you bring them in common focus, you don't get a coherent image by doing that. You can add the light together, but you can't produce a coherent image. They actually have to be optically coherent to do that. So with an interferometer, you have to compensate for that delay, and that's done with that OPAL cart, the acronym stands for Optical Path Length Equalizer, and you can instantly forget that. The OPAL cart actually slides along, and watch this. So this took me 4 hours to figure out PowerPoint to make it. And I couldn't reproduce this particular crime. But anyway, I'll show it twice because so much work put into it. But it's actually inserting a delay in the beam of light from telescope number 1 to exactly match the delay in the blue indicated at the right. And when I say exactly match, the criterion is about 1/10 of a micron, about 1/10 of a thousandth of a millimeter. And if you don't do that, it won't work. And that takes a lot of precision, a lot of computer control to do it. And this was known to people in the late 19th century, and they were as smart as, probably smarter, well, certainly smarter than I am, but they did not have the technology. There were some early experiments in interferometry that failed because of hitting the brick wall of lack of control to this sort of precision. But if you do it, you can fool the starlight into thinking those two mirrors are on the surface of this parabola. We do it with 6 telescopes at a time, and so it's as if all 6 are on that surface of a parabola. This was invented, interferometry was invented by this fellow, Fizeau, a Frenchman, and my French colleagues always point out that it was Fizeau who started this, not Albert Michelson. Michelson usually gets the credit. But he did some experiments all the way back in 1868 and did some experiments in Paris and at Meudon that were suggestive but not very demonstrative. It really was made successful by this gentleman, Albert Michelson, who was the first American to win a Nobel Prize in science, not the first American to win a Nobel Prize. Can you recall who that was? It was the president. It was Theodore Roosevelt, won the Nobel Peace Prize, but not a science prize. Before we went off and started the Spanish-American War, it was for another activity. But Michelson did some experiments at Lick Observatory and with small telescopes to test Fizeau's activities and showed that interferometry works, measure the diameters of the moons of Jupiter with interferometry, and it worked very, very well. And he was contacted by George Ellery Hale, who I got to be a great admirer of during my years of involvement with Mount Wilson Observatory. Hale, established Yerkes, Mount Wilson, Mount Palomar. He established the American Astronomical Society, the Astrophysical Journal, the National Research Council. This man was a superhuman in terms of his drive and his accomplishments. And he also had psychotic problems at the same time, so he was tormented by all kinds of problems, but just an amazing fellow. He was always driven to build the next larger telescope, and did so for 3 generations of telescopes. Hale contacted Michelson after he'd read about Hale's experiments in the astronomy journals of the day, invited him to build an interferometer to use on the 100-inch telescope, which was just it was nearing completion at the time. And Michelson jumped at the chance and built this interferometer, which attached to the front end had 2 mirrors that used the 100-inch optics as a beam combiner, basically to do to make the starlight think it was being intercepted by mirrors on the parabola. And it worked. He had a baseline of 20 feet. He was able to resolve a couple of supergiant stars, and some other experiments measured some binaries. And this was really a wonderful beginning of the field. And the gentleman sitting on the observing platform there at the 100-inch telescope, which still exists in the same way, nobody's actually been killed falling off of it, but it's very, very dangerous. So here is the only known photograph of Michelson's 20-foot interferometer atop the 100-inch telescope. And he used it for a few years. It was taken off the telescope, wrapped in burlap about 1925, and tucked away. I was lucky enough to get observing time on the 100-inch telescope. I was one of the last observers to use it before it was closed by the Carnegie Institution of Washington, and was actually the first observer to use it when it was reopened 6 years later by the Mount Wilson Institute. Never in those days thinking I would ever take over the Mount Wilson Institute as its unpaid director. It's a nonprofit, and I can assure you it's a very, very nonprofit enterprise. But it was fun for those years. But I saw this with my graduate student Brian Mason, who's now at the U.S. Naval Observatory in Washington, and it was stuffed in the rafters about 20 feet off the ground. And Brian and I, somebody said, "We think that's the old Michelson interferometer." Brian and I crawled up there. It was filthy. We pulled back the burlap, and I felt like Howard Carter peeking into Tutankhamun's tomb, looking in there and seeing this thing. In addition, there were about 100,000 generations of mice. The evidence of their presence was there, as you can imagine. And Hanavirus be damned. We opened it up more, and it was a beautiful instrument. I thought, wouldn't it be wonderful to take this out and put it on exhibit? And we did that eventually. When CHARA built our building up there, I got a physics alumnus from Georgia State, talked him into donating money for a little exhibit hall, and the 20-foot interferometer is the centerpiece of that exhibit hall. And I think we lucked out. That's the biggest crowd that's ever been in that exhibit hall. But they're not photoshopped in. Those are real people who were there. We have it sticking up from the floor. And one of another graduate student, Nils Turner, suggested, why don't you put it, rather than having it just sticking vertically, can it so it looks like the telescope looming up out of the floor, and we did that. So it looks like it's pointing off to the southwest or something like that. But that's actually the original prime focus observing cage of the 100-inch. If you've ever been to the Air and Space Museum in Washington on the National Mall, the Newtonian cage is on exhibit there, and it's got a Hubble mannequin, and it's set up as if Hubble is observing there at the Newtonian focus. And that's on long-term loan, which was a real headache because of one famous astronomer not wanting it to happen. But that's more to be told over a beer. So anyway, I was pleased to put that on exhibit. That sort of closed the loop of CHARA historically with Mount Wilson in interferometry. And I'm pushing the button. There it is. So Pease decided to build a 50-foot interferometer so he could resolve the diameters of more stars. And he built this thing, and the gods of technology decided to make an example of Dr. Pease, and it was successful out to 20 feet. And which was so he could replicate some of Michelson's measurements. Beyond that, the technology, the flexure, control, the doggone thing failed. And he worked at it for 4 or 5 years, said to heck with it. And it was a standalone instrument. Facing east-west, it has a polar axis. It was very, very beautifully designed, but it just did not have the level of stability that was required. And this next picture that you've already seen, this one sets the stage. This was the level of technology they were dealing with. And this is circa 1925. The instrument was locked up in its building, and when I first started observing there in the 90s again, doing spectral interferometry, the guy who was the mountain superintendent decided to sell it for scrap. And I thought that was sacrilege. But anyway, it was sold for scrap. This is the way we install telescopes for CHARA. And so I like to show this because it shows the advantage we had of technology. I mean, a helicopter is not precision. Well, it is precision technology. But we were able to, come along many, many years later, 75 years later, with a lot of progress under other people's belts and get this job done. So here is what we have built on Mount Wilson. You can see the 100-inch telescope there in the center, the 60 inches off to the top, so this is flipped around from the other picture. And everything outlined in black there is Georgia State property. The Mount Wilson site, by the way, is national forest land. Actually, a few years ago, President Obama designated that area of the Angeles National Forest as a new San Gabriel's Mountains National Monument. So it elevated its status, but no extra money has yet to be put into it because of that name change, and who knows when that might happen. But anyway, eventually it will pay off. So we're sitting on federal land, and which has its advantage. The advantage is you don't have to pay rent on it. The disadvantage is they can tell you what you can and cannot do. If you want to pick up a blade of grass, you have to get a permit to do that. It's not that bad, but they're actually very nice to us. So we have a really big impression on the mountain. How many of you have ever visited Mount Wilson Observatory? Any of you? Oh, you should go. To me, it is the, if there is an astronomy World Heritage Observatory, it's Mount Wilson. If you think about what was done there, it set up all of modern cosmology, the expanding universe discovered there, all the modern stellar astrophysics, stellar spectroscopy made big headway. The first modern telescope was the 60th telescope there. Just so many things were done there that to me, it's more important than the Hubble Space Telescope. And people from NASA would kick me in the shin for saying that. But the Hubble Space Telescope was not named Hubble for nothing. It was named after the gentleman who did his work on Mount Wilson. So it's a wonderful place, and it's still going strong. And the major science project there is ours. The observatory lets us be there. We pay them a certain amount of money a year, and there are other facilities up there. But the 100-inch is now only used for observing, public viewing. And that was one of the things I did in my last years as director, was to start a project to enable you to actually look through the 100-inch telescope without standing on that little diving board, because we couldn't afford the insurance to do that. And so we added optics so you could actually stand on the floor underneath the telescope and look through it. Or if it's over at some steep angle, you climb up on a small ladder. And you can rent it out. It ain't cheap, but organizations can rent it. But you can get exquisite views of things. You see, if you look at a globular star cluster, you see the colors of the stars in the globular cluster. There's so much light gathering power. A lot of photons are crammed into your eyeball with that. So, but that's not CHARA. That's another story. So the mountain is quite crowded, and so we had to build this facility to coexist with these existing facilities there without damaging their world-class nature. And we did that, I think, and did it pretty successfully. Here's an aerial photograph that shows our telescopes. If you look at the 100-inch, you see that long building, that long skinny L building running horizontally and then up. That building is the beam combining laboratory for CHARA, and it's almost 100 meters long. So it's a big, long facility, and most of that is occupied by those opal carts, the optical delay line, the delay line compensators. We'll look inside this in a minute, and you'll see them. And so there's a lot of overhead in an interferometer, and it takes a lot of mirrors, a lot of optics to bring the beams together and make it work. So that simple PowerPoint cartoon I showed you is a very simplistic depiction of the whole thing. In fact, here's a layout of the optics of the array. It's been modified. This is an old diagram. But so you see the 6 telescopes. There are 2 arms in a roughly Y-shaped array. And there are rules. You have to obey some polarization requirements, otherwise you won't get interference, and a certain number of rules. But it takes about 20 mirrors to bring the light together before the interference happens. It also passes, we send the light from each telescope along the ground through tubes, which 99.9% of the air has been evacuated, to avoid ground level turbulence. The ground level scene would totally whack it, would totally destroy its performance. And so we do that with vacuum tubes, which to those of us my age, you think of things that you plug in old TVs and radios, right? Vacuum tubes. But these are tubes from which the air has been evacuated. And so they have windows, thick windows on either side to withstand the atmospheric pressure differential. There's just a lot of overhead. And every time you bounce light off a reflective surface, you lose a few percent of light. So if you have 20 reflections and you're 95% efficient, then the amount of light you get through is 0.95 to the 20th power. It ain't much, folks. So these things lose sensitivity because they're so inefficient. And I used to, at our staff meetings, I would say, if any of you can think of a way to get rid of a mirror in this optical terrain, I'll buy you a nice single malt scotch. I never had to buy anybody a bottle of scotch, so I didn't disrupt anybody's habits there. I would have gladly done that. Bought them a case. Okay, so here is an overview. You can read the Y-shaped. We have the world's longest baselines. There are two major interferometers in the world. There's the one that was the most money has been spent on is the European Southern Observatory. It's an international facility called the Very Large Telescope Interferometer, VLTI. And one of their beam combiners cost much more than our entire facility. We out-resolve them. We have longer baselines. They have larger aperture telescopes, so they can see fainter things, so we complement each other. They're also in the southern hemisphere. They're located in Chile, and we're in Southern California. But we outperform them with a fraction amount of money. I'm very proud of that. We're just a small state university. Actually, we're not small anymore. We're like the 7th or 8th largest university in the country by virtue of absorbing a junior college system. It's crazy. But I'm rambling. Our telescopes are 1 meter apertures. We have 6 of them. My successor is CHARA director Doug Guys. His goal, he's going to set out to fulfill a goal that I really wanted to do long ago, and that's get additional telescopes. And we built it so that it could accommodate 2 more telescopes. So we'd like to make it into an 8 telescope interferometer. And I'm optimistic he'll do that. We operate in the visible part of the spectrum and the near infrared, the so-called K-band, HJ and K-band infrared. And it's a star machine. We're interested in sizes and shapes, features on stars to determine fundamental stellar properties. And so we're going great guns with that. The timeline, we broke ground in '96, and I could write a tearjerker of a novel about how we got our site and how we lost sites and intrigue and so forth. We actually got our funding from the National Science Foundation before we had a site, which is quite embarrassing. We thought we had one, and that went south really quickly, for good reasons, it turns out. So we broke ground on Mount Wilson in '96. We got first fringes in '99, and we did that early because the Keck Foundation was going to give us money for a 6th telescope. The NSF funded us for 5, and they wanted to make sure we could get fringes. They logically wanted to make sure that they would work before they invested their money in us. And so we set up and got fringes on a pair of telescopes, and I wrote them a 1-page letter, sent them a diagram, and they sent $1 million check back. It's the most effective letter I've ever written in my life by far. So we stopped operating in '99, and we finished the rest of it off, installed all the telescopes and the first optics. We got our first routine observations going in 2005. We produced our first images in collaboration with a group from the University of Michigan in 2007. And the last count, we've now published almost 150 refereed papers, mostly in the Astrophysical Journal. We have 5 or 6 Nature papers now. We're doing really, really well. I'm very proud of it. And so I'm CHARA's greatest cheerleader in my retirement. Okay, 143, 150 just around the corner. So here's a little tour of the equipment before we start talking about science. Here are the telescope enclosures. We actually made these. We didn't call them buildings because we didn't want to have a lot of things that LA County would have required us to have in terms of human access, like handicapped restrooms and elevators and things like that, which we couldn't afford. So they're called telescope enclosures, but they're in 16-foot domes. Now, we have a 16-inch telescope in an observatory at our university in Atlanta, 50 miles east of Atlanta, in the same size dome. These are 40-inch telescopes inside these domes. So they're really compact telescopes. They're beautiful telescopes. You can look at the picture, a cartoon to the left, a CAD drawing to the left, a photograph to the right. I probably, it's fair to say, they're the highest quality ground-based telescopes ever built. These would be good space telescopes because we wanted to have really good optical wavefronts. Start off with good quality and then let the atmosphere destroy it rather than have bad stuff made even worse by the atmosphere. And we got our optics in Russia, and we came along at the right time. The Soviet Union had gone down the drain. Russia had a very large optics enterprise to supply their physics and astronomy and whatever their DoD, whatever the Russian Defense Department was called. And there's a thing called the Leningrad Optical Mechanical Works, LOMO, which was really built to make spy satellite mirrors for the Soviet military. And so LOMO shut down, and they had a lot of high-quality opticians. They had some representatives in the U.S. who were expatriate Russians who were selling their services at about a fifth the cost of high-tech American aerospace companies. Now that is politically very bad. To go to Russia to buy your optics would be even worse today, I guess. But we couldn't afford it, the high quality we got otherwise. The scary thing was if they don't deliver, who do you sue? So good luck with that. They did deliver and either met or exceeded spec on all 6. They were so cheap, we bought a 7th optical set, primary and secondary set, so we have that in the bank, so to speak, for an additional telescope.
Did you place the order all at once, or did you wait to see?
No, we had to place it at once, otherwise we wouldn't have gotten. It was a real big risk, and if it hadn't succeeded, you never would have heard me again. So I would have fallen on my sword a long time ago for that. But that was the biggest risk we took, but we didn't pay for it. Of course, we made progress payments, but we had to place the order, and of course, if we didn't pay, who would they sue? So I guess we were protected in that event, but it worked very smoothly. This gentleman is Dr. Laszlo Sturman, who is a PhD astronomer, but he's really an exquisite engineer, and he has made so many upgrades to the mechanical and optical systems. But here he is using one of our mirrors as a nice shaving mirror. But I could talk for 2 hours about these telescopes. So anyway, Laszlo is looking at the mirror. The light, each telescope is injected into these vacuum tubes and sent off to the central station. They're collimated beams, parallel beams of light. They don't come to a focus, actually ever, until they have interfered. They interfere as pupils, not as a focal point. So looking out across from Mount Wilson, you can look at our beam combining laboratory. We have mirrors inside giant boxes that where the beams are turned to make parallel to one another to send down to the delay lines. And you look at this and you can see the delay lines going off in the distance. At the end of the building, there are these retroreflective mirrors. It's a cat's eye optical system that has certain nice properties. And so we have each of these is a 2-pass, it's 68 meters long. And it goes 2 passes, so you get 2 times 68, which I used to be able to do in my head. What is that, 136 meters of path difference correction. So it's all done with mirrors, and I won't go into that except another much more simple PowerPoint trick than the previous one. We actually ordered these delay line designs from JPL, who are neighbors at the foot of Mount Wilson, because they had built some for a smaller interferometer some years before. They knew how to do it, so why reinvent that wheel? My philosophy was, if somebody knows how to do it, pay them to do it, or steal their ideas. And so we happily did both. But the ideas we stole were not patented. They're all open source. So here are some of the beam combining tables. They're sitting in a lab, which is on 24 inches of reinforced concrete. Mount Wilson is a little bit more than a stone's throw from the San Andreas Fault. So you could ask about seismic activity, and I would just smile and say yes, there is. And we've been there. Susan and I were sitting in our CHARA conference room chatting one time with the CHARA staff after a meeting, and I looked at her and she had this funny look on her face, and about half a second later I knew why, because we all started doing this. And so we had a little earthquake, and
things went silent, and the first word out of somebody's mouth was an expletive that I can't repeat, saying, we'll never observe tonight. And in fact, we did. So it shook a little bit, but nothing was misaligned, and we were up and running that night. That's not to say that when the big one comes, we'll be wiped out, but there'll be a lot more to pay when that happens. So here's a picture of our control screens. It's 6 27-inch monitors with one person can control the whole thing. And we have colleagues have control centers. We have one in Paris, one in Sydney, one in Ann Arbor, Michigan, and one in Nice, France. We have 2 French groups that collaborate. And so you can actually control this from if you know the password, you can control it. Fortunately, we're obscure enough so that whoever is hacking into important things in this country hasn't decided to do interferometry yet. Okay, so some science. So I'll talk about a list of things here, which I'll flip through. You can read, and I'll try to get you out of here early. The first thing we looked at, we decided it would be really neat to look at stars that rotate rapidly, because it had been postulated long ago that rapid rotating stars will, of course, obey the laws of physics. The surface gravity at their equators will be decreased by the centripetal acceleration. They'll expand, and they'll flatten at the poles. When they do that, when they flatten at the poles, the pressure at the poles increases, the pressure at the equator decreases, so they get brighter at the poles and fainter at the equators, just from the laws of physics. It's perfect gas law, basically. And so you would expect to see them darken around their equator, and that's a phenomenon called gravity darkening. So we looked at Regulus, which had been known to be a rapid rotator because its spectral lines are very broad, and you could measure the width of spectral lines and calculate the rotational velocity modulo the sine of the inclination of the axis of rotation to the line of sight. The V sin I was known, and so it was postulated that this star was whipping around really fast. So this was a good candidate. It's bright, it's nearby. We looked at it, and this is a model that we produced from data taken with CHARA. It's not an image, and so there's Regulus, which is oblate. But anyway, we see the oblateness. Regulus rotates once every 16 hours compared to the sun, which rotates once a month, basically, depending upon latitude. And so it's really whipping around, but the gravity darkening is at the equator, which should be longer than the other dimension. Now, since that time, we've made actual images in collaboration with our Michigan guys who built a beam combiner for imaging. And so here's a gallery of a number of famous stars that Altair is there, and others. Altair was actually the first image that we made in 2007. The first paper we published was a Regulus, but it was a model, not an image. Since that time, we've actually come back and imaged Regulus, and it basically confirmed our model, which is always a good thing. And since I'm not sure if we've done any other rapid rotators, but there are more to be done. But they all are in generally good agreement with the theory that would describe the extent of the gravity darkening. Now, you look at if you look at Aldebaran there, you see the bright spot. I told you that they get brighter at the poles. Mm-hmm. The bright spot is not at the pole because of another darkening effect in stars called limb darkening, which has to do with looking at the edges of stars, and you're looking through thinner atmosphere higher up, and it's a phenomenon we see on the sun, which is completely spherical. So people have looked at that and they said, aha, that's not at the pole, but we understand why it appears to be brighter at a lower latitude from the pole. One star, Beta Cas, we're looking at nearly pole-on. It turns out, by the way, that Vega, the third brightest star in the sky, is a pole-on rapid rotator. And we've made measurements of that, and it totally changes ideas about the basic physics of Vega. For a long time, it was a standard star, and it was one of these things where you pick a standard star for photometry, for measuring brightnesses of stars. That's not at all standard because it's a rapid rotator, and it is a highly oblate thing, but you don't see it because it's rotating pole-on, and its spectral lines are not broadened. So it has a small V sin I, not a large V sin I. Okay, we cannot yet image planets around other stars. And I say yet because there is a chance that as we're now adding adaptive optics to our telescopes, we have new, better detectors that essentially have zero pixel noise. And so there's a chance we may be able to directly image some of the hot Jupiters around stars and some brown dwarfs, but no Earth-like planets. What we can do, though, is we can look at the host stars that possess planets in orbit around them, measure their diameters, and that's an important thing to do because then we can determine their surface temperatures, and we can tell which of the planets orbiting them are in life habitable zones. So if there are little green men, little green women there, whether or not they could actually take nice, breathe the air like we can. Basically, whether or not water exists near the triple point. That's a criterion. And this is a case of one 55 Cancri that has multiple planets. Some are, the Goldilocks analogy is often used with exoplanets. This one's too hot, this one's too cold, and this one's just right. In this case, they're either too hot, too cold, or just right some of the time. And by that I mean there's at least one planet that orbits in an eccentric orbit. Sometimes it's in the habitable zone and sometimes it's not. So go figure. That's a good candidate for life someday. There are stars that have been known since the early 20th century called emission line B stars or BE stars. And they show strong emission lines in their spectrum of hydrogen gas. And it was postulated relatively early on, 30s and 40s, that this light comes not from the star, but from shells, either shells around them or from disks around them. And I mentioned him already, Doug Guys, who's now the CHARA director, is a world-renowned BE star expert. And so Doug got very interested in using CHARA to look at these stars. And we've actually now imaged disks around BE stars. The shell theory long ago disappeared. But they have substantial disks. And so here's one Gamma Cass. And this is actually a model, not an image, to be accurate in advertising. This is my favorite, the one on the right, Zeta Tauri, is one where the disk is edge-on. And if you look at that, you can see the scales here. This is, the scales are in milliarc seconds. So the stars themselves, their radii are a couple of tenths of a milliarc second, which if I slow down and think about it, just floors me that we can see detail like that so fine. This one, Doug and a postdoc, Gail Schaefer, looked at this a number of times, and they found a very odd thing, that the position angle of that disk was changing from time to time. And in fact, when they put these together, and the translation from my Mac to this Windows machine, the embedded movies don't work. But it actually is a disk that's precessing, because there's a companion in there that's disturbing it gravitationally and makes the thing precess in time. So I think the next slide would attempt to, well, hey, that one's going to work. Very nice. So you can see the little stellar companion is orbiting in that plane above and below it, and its gravity is causing the disk to actually precess. And that was totally a serendipitous thing that we found. Doug also found, by the way, that Regulus has a companion, which is a white dwarf, which had never been known.
What is the time scale of that precession?
That's a good question. It's of the order of weeks. It's fast. So it's quite fast. So remember I said at the very beginning of my talk that I was wanting to be able to see binaries go around while I was still alive. One of my PhD students that was looking at binaries, trying to do a survey of the frequency of binaries and produce a really important dissertation from that results. One of the stars he did along the way, he looked at this system, Sigma Corona Borealis. And Sigma Corona Borealis has 1, 2, 3, 4, 5 stars in it. It's a hierarchical quintuple system. And the shortest period one is the one down in the lower left, Sigma 2 Corboreal, has a period of 1.14 days. And he actually was able to calculate the orbit, watch this thing go around once a day. And that's faster than I ever dreamed possible. But so that goal has been fulfilled. But you can see that the periods range from we don't know how long the period is of the widest pairs, But the one from between sigma 1 and then the double in the lower left is almost 750 years. So this is how nature can build these wonderful, complex, multiple star systems in a so-called hierarchical and very stable system. They're stable for a long period of time. Shortest period binary ever resolved is 2 stars. Very famous contact binary, Beta Lyrae, and we resolved Beta Lyrae. These are actual images of the star. It's a star that's called the Roche lobe configuration. They're so close that they don't see each other as point sources. One star extends out towards the other. It has exchanged mass in episodes in the past, and we see that, and it has a period of about 13 days. It has an angular separation of about a milliarc second. The semi-major axis of 0.9 milliarc seconds over there. So we only have these 4 images. The next slide would be a movie of them going around. And it's an eclipsing system, and you can see them moving around in the plane. What's the other really famous bright eclipsing binary? Algol, that's right. So Algol was another good target, and if this worked, you would have seen a movie of Algol going around. So look at my slides on the Mac and you can see it. And both show the Roche lobe configuration of one of the components. Now, a few years ago, geez, already too many years ago, the star Epsilon Aurigae is famous, but every 27 years it goes into eclipse. Only every 27 years. Very wide system, but it's the plane is exactly in our line of sight. So every 27 years, a companion passes in front of the star, and it's a mysterious companion. It's dark and it's extended. And I was contacted by the Epsilon Aurigae expert of the world, a guy named Bob Stencil at the University of Denver, back about 2007, who said, "This is coming up, CHARA needs to look at this, would you do it?" And I said, "I remember the star, and yeah, sure, we'll do it." And we did it, and we watched it for over a period of almost 2 years. And you can see on the upper left is the uneclipsed star. The second picture is a dark disk coming in front of the star in November 2009. There it is a month later. The disk has progressed. February 2010, August 2010, it's still going on. And all the way a year later, after 2009, the eclipse is still going on. And we have other pictures afterward where it has ended. And so we watch the first images, and these are actual images we produced from the interferometry of this marvelous and weird system, Epsilon Aurigae. It's a giant star that has a stellar companion that is embedded in an optically thick disk. You cannot see the radiation from the star itself. It's completely hidden in this very thick, very oblate disk that lies in the plane of the orbit. This is another picture that shows the illumination is not so good. If you look at the bottom, you can see a little bit of the starlight. You can see some of it in the upper right there. But this is from the perspective of the disk. Imagine the disk is stationary, and that's the star sort of streaking behind the disk there. Looks like a couple of hamburger buns, but that's not what it's actually the star silhouetting itself against the disk. Now, one of the great things about CHARA that our competitors in Chile, the European facility, has, is that we're very flexible. Something interesting can happen and we can kick people off the telescoper's schedule and say, "We're going to look at this and we'll give you time later." The Europeans won't do that. And a nice nova went off in 2013, Nova Delphinus, that we got on within 24 hours of detection of the outburst. And the plot here is the time since the outburst was estimated to have begun. The outburst itself wasn't seen, but it was detected probably the same within a day of it happening. So we jumped on it and started observing it, and there it's its angular diameter. And so we're actually we're measuring the fireball of the nova expand with time. And you recall that a nova is a binary system that contains a white dwarf and an extending companion. And the extending companion dumps hydrogen to the surface of the white dwarf when it gets yay deep. The surface gravity at the bottom, because of the enormous gravitational pressure, the hydrogen at the bottom undergoes thermonuclear fusion, and it goes boom, and it blows off this small, shallow ocean of hydrogen, all on fire, expanding around it. and the star lives to do it again. So these things actually recur over time. But it must make a heck of an impression on the companion who's dumping his white dwarf, his hydrogen on there. But if you look at the plot, you can see it's expanding fairly uniformly, and then it goes out to about day 28, and it goes kind of wacko. And what happened at day 28 was that the fireball became non-uniform. It clumped. In fact, a lot of dust started forming, and we see that in an accompanying plot. Those are images, by the way, of the fireball. We saw evidence in the, all of a sudden, the color of the star in the infrared becomes very, very bright, which means it's got a lot of hot dust has formed because of the temperature and density. The chemistry is right for these graphite grains to form. Okay, so we're getting near the end here. This is more recent result. This is a supergiant star. It's an M21A. These are the Antares class objects, solar system class size objects, very far away, 16 kiloparsecs away. It's bright enough to see. And here's the size, 4 milliarc seconds, and we see spots on it. It has a very complicated surface, and this sort of structure on the surface had been suspected for another supergiant called MIRA that was imaged with a far infrared interferometer, also on Mount Wilson, built by Charlie Towns, Nobel Prize winner for inventing the maser, led to the laser. Charlie was an astronomer at heart. But we see these things, and they're called convection supercells. It was a astrophysical transport theory to get the radiation out from the center efficiently. And so this is the first image ever made of these kind of supercells for this wonderful big star. And here's another one, lastly, showing spots on Zeta Andromeda, which is a giant star in a projection map like this. And our goal for this one, if we get enough observations, is actually make a movie of the star rotating and the spots coming around again. They have enough lifetime to do that. They're big stars, but they rotate relatively rapidly. The star is not oblate. This is it's a projection onto a surface map like this. Okay, our next to last slide. I have to brag about it again. Highest resolution telescope ever built. I would have thought by now that this country would be building a super interferometer with 25 4-meter telescopes with baselines of 10 kilometers to look at the black holes in the centers of galaxies. But that's not happening, and because there's just not enough money to do that sort of thing. Someday it will. Maybe we will build it on the moon. The moon would be a great place as long as you don't kick up the dust. We own it, we operate it, partially funded by the National Science Foundation, but mostly by the state of Georgia. If you've ever bought a lottery ticket in Georgia, by the way, the Georgia lottery contributed $2 million to the CHARA. So you never think about buying a lottery ticket supporting astronomy. They don't do that anymore. The legislature doesn't let that sort of thing happen anymore. The legislature decides where the money goes. We have collaborations with these folks, which all give us nice places to have annual meetings. Although this year they cheaped out and did it in LA, of all places. The previous year was in Nice. We're upgrading with adaptive optics, compliments of the National Science Foundation, and a lot of proposal writing. And we just got a grant from the NSF to expand CHARA to the U.S. community by providing up to 50 nights a year on a competitive basis for astronomers from anywhere. When we've been giving away about 15 nights a year, and we formalized it to our advantage, and we hope to the U.S. Astronomy advantage. There's a world of stuff to be done, and there are a lot of smart people with good ideas. My writing, I'm not going to say much about that. I've written a novel. It has 17 reviews. Look at those stars. I only wrote 14 of those. 2 other people really liked it. It's a hero astronomy adventure thing that I had a lot of fun writing. It took me about a decade to write it. I would go fits and starts, but helped pass a lot of time on. I might have even gotten started on. No, it didn't go back to Eastern Airlines. It was all done on Delta. I have a prequel and a sequel, but who knows? I also, when I was director Mount Wilson was threatened by a forest fire, the station fire, for about a month. It was a hellacious thing, literally. Very hair-raising. Susan and I went out there. She has a video on YouTube of us driving up in the mountains with a police escort right after the fire along the Angeles Crest Highway had been put out. But so I created a blog that had a lot of response, and we raised, somebody said, why don't you ask for money? I said, sure. So I started asking for money. We got about $60,000 in donations from folks just concerned about how the observatory was going to restart, hopefully after the facility the fire had been cured. So these are both Kindle books. I'm now working on a walking tour book of Mount Wilson that you can use on your iPhone to walk around, and you can cheat the observatory out of the $5 they charge for their book. And then I inherited a lot of stuff, and this is a long story, but my mentor in Chattanooga was this gentleman, and I have thousands of pages of writings that he did, he never published, and I have thousands of negatives of incredible things that he photographed starting in the 20s. Machu Picchu, famous astronomer. I tell Susan that it's a huge burden to make something out of this. And now my biggest thing, in 1977 I wrote a Sky and Telescope article about my speckle work. 20 years later I wrote another one, and another 20 years has elapsed, so it's time for me to write a 40 years article, and I'm already 6 weeks late with getting that back to them, but that's what I'm up to. And the last thing is the camera that we use for spectral interferometry is now at the Smithsonian Institution. They asked for it, and wow, it's a thrill, so they've had it for about 2 weeks. That's it, folks. And I appreciate your attention, but if you have a few minutes, I'll be happy to take a shot at some questions. Thank you. Yes, sir.
Really nice presentation. What are you doing? Maybe I missed it somehow. What are you doing with regard to the polarization of the light? Do you sense that? Do you put polarizers on all your scopes?
We don't. My comment about polarization, what do we do with it, is that if you bounce a mirror, a beam of light off at an angle, of course you introduce polarization in the beam. In order to get interferometry, you have to introduce the same polarization into every beam of light in the same sequence. And so we have these beams coming in from 3 different directions, and so the trick is how do you introduce the polarization the same way? And what it does, it costs you more reflections. So you add dogleg reflections that treat them all in the same way. But we don't measure the polarization, but we have to align our mirrors to within, minutes of arc in order not to have polarization losses in the beam. But that's a very good question.
But you say you can see, when you look at sunspots on distant stars, you can see the polarization effects.
We could, and people have suggested, why don't you make some polarization measurements? And that's a great idea, but no one has taken it up. Somebody has to take it under his or her wing, and that hasn't happened. Good. Maybe that'll happen. Some of these bright astronomers come in with our 50 nights a year.
So you can just put rotating polarization plates on each of the scopes, have them each rotating in separate.
You could, yeah, you could. Could you put polarization plates on each telescope and rotate them and look at what happens? You could, and I'm sure you would see effects, particularly with stars with disks and things like that. But we just haven't done it. It's a great idea. And I'll mention that to Doug Guys. Say, Doug, go do it. I don't have to worry about it. Yes?
You talked about the rapid rotation, like on Regulus, which the equatorial part is less dense, and the polar parts get flattened, so they get more dense.
Right.
So I don't completely understand how that affects the emission of light.
What happens is that as the surface gravity is stronger at the poles than it is at the equator. So the gas pressure is higher at the poles than it is at the equator, and the temperature of the gas is lower at the equator than it is at the poles. Mm-hmm. So if the pressure is less, the temperature drops. And as a result of that, if the temperature is less, you get less light. It doesn't change the spectrum of the light, but it appears to have a dark band around this equatorial bulge.
Can you do quantitative measurements of that difference in intensity?
You can, yes. And that was one of the things we did because that had been estimated, and we find that it agrees with what people had built in their models to within our error bars. So there apparently there's no unusual physics going on that isn't understood. So you'd rather find something that messes things up rather than supports ideas. But another interesting thing we did, I didn't talking about oddly shaped stars, is Cepheid variables pulsate. And so we've looked at a number of Cepheids and measured their diameters and watched them pulsate. And there's a trick there. You can see them pulsate spectroscopically in the line of sight. We look at their photospheres from an angle, but it turns out that the spectral lines are not coming from the same depth of the atmosphere as is the light we see in the photosphere when we measure. And there's a factor there called the beta factor that compensates for that, and the value we're getting is not quite in agreement with the theoretical value. So we think there we're challenging the theorists to go back and worry about that particular problem.
I like your icon and the use of Orion. Did you choose that because of the symbolic idea of the hunter, or because you like Betelgeuse?
I stole that. My first employer was Kidd Peak Observatory, operated by the Association of Universities, ARA Incorporated, and their logo has Orion on it, and I thought that's really neat. And so, like I said earlier, I steal other people's good ideas. And also, one of my binaries that is named after me that I discovered is a star in Orion's belt. So. Well, thank you very much. It was a pleasure to be here. And visit Mount Wilson.
You cannot leave